Good morning, good afternoon, and good evening. Thank you all for joining. My name is Molly Helmuth, and I lead ICF's International Climate Resilience Workstream. At ICF, we have the largest and most experienced team of climate change adaptation and mitigation professionals in the world, and we work to support climate resilient low emission development, including the use of Earth observation tools to inform decision making. ICF recently supported NASA's prediction of worldwide energy resources team to think through the most impactful investments to maximize power's reach and societal benefits. I'm excited to be here with NASA to facilitate this very important event that showcases power in action. For today's session, we will begin with a brief introduction to NASA Power from Laura Rogers, Associate Program Manager at NASA Applied Science. Laura leads the strategic planning efforts for the ecological forecasting and climate programs within NASA Applied Science. Then we will get a live demonstration of NASA Power from Paul Stackhouse, a senior research scientist at the NASA Langley Research Center who leads the Power team. During the live demonstration, there will be an opportunity to ask clarifying questions. Madison Brodel, a geospatial data analyst and outreach coordinator for the Power Project team, will be scanning the chat for these questions. This live demonstration will be followed by a 20-minute question and answer. You can either put your questions directly into the Zoom chat, where we will be monitoring them, but you will also be able to unmute and ask questions directly during the Q&A, which will follow. Last but not least, we'll finish the session with a brief summary of the event. Without further ado, Laura Rogers will introduce NASA Power. Laura?
Thank you, Molly. And a huge thank you to the entire ICF team, Rob Kay in particular, and the Resilience Hub for hosting this event. Good evening to everyone in Scotland, and thank you to all who have joined us across the globe. What a wonderful event these past few weeks have been, and they've both been energizing and exhausting. It's a pleasure to be here, though, to introduce NASA Power, or the Prediction of Worldwide Energy Resources, which is largely funded and supported by NASA's Applied Science program. NASA Power is a true example of bringing together research through global Earth observations and using the latest technologies for data fusion, machine learning, and geospatial analysis to transform data into knowledge. As I've listened to the pledges being made here this week, focus on clean financing for developing countries, a reduction in methane emissions, and commitments to environmental justice, I get energized and excited. We're on the cusp. But I also look to many of the pledges and where we sit today, and I see a gap, and energy transformation is needed, a shift in the S-curves. And why does this matter? Why does power matter? To meet our shared commitment of the Paris Agreement goals, we must move toward clean energy about 5 times faster than at present. There's a big opportunity here. Solar and wind power are now more accessible than ever. The sector is generating more jobs and giving us cleaner air. As Molly mentioned, we first met her and her team at ICF 2 years ago because we, NASA, needed to develop a business plan for power. We aimed to understand the critical investments we needed to make and how those investments could impact our climate and society. An understanding of how to accelerate the transition to clean energy, generate jobs, and provide cleaner air. We came out of this on the other side of this planning exercise with a real understanding of where we could make small changes for minor impacts, but also where we could truly make the leap in the next S-curve and advance each of the markets served by power exponentially. Power not only serves the renewable energy market with solar and wind resources, but also the sustainable building and infrastructure market. Power can now inform how designs will withstand the shift in climate zones, and climate modeling can inform building energy codes and heating and energy costs. The agroclimatology sector is another growing user of this information. Global food demand is increasing, resulting in larger investments in agriculture, but these investments are often limited by a lack of data-informed decisions. Power delivers freely available, geospatially enabled, high-quality, trusted information to users in formats they can use immediately. With that, I would like to welcome Dr. Paul Stackhouse. Dr. Stackhouse has led this initiative for approaching 20 years and has truly been a leader ahead of his time. Paul, please take it away.
Well, thank you, Laura, and thank you also Molly and Rob and the ICF team and also the Resilience Hub for giving us this opportunity. This presentation here is a story map presentation, and we have provided the link to this map on our chat, and so that you can review this at any time, and I presume also the recording of this will be available as well. And so this is the Power Project, and what we hope to do today is give you an introduction to the sorts of data products that we have from Earth observations and how we've improved those in time, how we assess those products, how we've made them available and you can access them, and then how users have used them and to obtain some real benefits for real decisions in this world. And finally, we'll provide some extra information on how you can even learn more. So with that, I'll move into our first section, which is an introduction to our Power Project. And also we're just starting broadly to introduce NASA itself. I mean, why would NASA be interested in this applied science sector of energy and even agricultural information? Well, it's because NASA has made a national investment or received a national investment to develop Earth observing capabilities. So we've developed satellite instruments that measure various aspects of the Earth's atmosphere, its clouds, its gaseous constituents, its aerosols, its surface properties. And there's a number of satellites. This diagram here identifies various different satellites, some of which I'll mention today, in time, and then even goes forward into some of these future planned missions. And so we here are adapting and customizing information from these observations to make them available to the applied science community. And so there's an applied science program within NASA Earth Science, and that program supports the work. And you can click on this link to learn more information about that program. For us, the Power Project is an applied sciences project that takes the Earth's observation data related to the estimate of the solar irradiance and even other what we call radiative quantities, which is energy either in the solar wavelengths or in what we call the thermal infrared wavelengths. And we study that information to understand the climate and its and the actual energy that powers the climate in terms of the amount of sunlight that enters into our atmosphere, how much is reflected out. And we, as part of that, compute the amount of solar radiance to the surface of the ground. And so that information, plus a variety of other information from NASA Earth observations and/or modeling analysis, is utilized and provided to the public in these three areas. First, the renewable energy development to improve the adoption of technologies and feasibility for renewable technologies for clean energy. And then also the building energy efficiency and sustainability needs to monitor the building performance in energy terms, and is there a way to improve that energy efficiency for existing buildings, and then plan for feasibility for future buildings. And then some agroclimatological applications such as crop modeling or other decisions that have to be made during the course of raising or even locating various crops in various different climates. So the Power Project helps communities become resilient amid observed climate variability through the easy access of these solar and meteorological data via a variety of access methods. So our main website is here, and that's our homepage. And from there, you can link to that. And then we also have a data access viewer, which we'll show you later, but this is a snapshot of that will help you obtain the data products, which we'll talk about a little later. In terms of Power's history, Laura mentioned that we've been doing this for 20 years. We actually started way back in the late 90s when the National Renewable Energy Laboratory asked us for information over Africa to help refugees justify funding grant to place solar cooking and also eventually solar refrigeration capabilities in places that they were totally disconnected from the grid and from any other natural electricity sources. So from there, because we were a global data set, we were able to provide information on that global context. And from there, in time, we were able to add that sustainable building community. While we go through the history here, I just wanted to point out that at the bottom here, we have a figure that shows the increase in installed solar energy capacity of the world. But also compared to that is our growth in terms of the number of people who asked for data, who made data requests that we were able to fulfill through our web services. And so what we've done is we've changed and evolved in time, improving both our data sets and to those that we reach out to. So after adding some parameters for buildings, we then started to work with the agricultural community. Then we added near real time in terms of a week behind real time for all these quantities on a global basis. And you can see the number of total requests increasing every time. And then we go to the enhanced climatology. And then recently we've added all these GIS capabilities. And now most recently, our latest version, which we just released a few months ago, also features hourly data. So now we have expanded the amount of data which we do hope attracts even more users and more development and the use of this information. And just to show you, this is a logarithmic scale, and the amount of users in time has been going up logarithmically. And so, but as Laura mentioned, to really get to an energy transformation, we need to even accelerate this growth. And so that is what our purpose here is to continue to try to develop and improve the types of data that we provide. So let's first go through the sorts of data sources that we do have through our current projects. And we're featuring an Earth observations from a variety of projects that I'll describe here in a moment. And the underlying source of these are have evolved in terms of the ability and the various different versions. And we've of course, I mentioned the near real-time capability, which is at this point within a week of real time to provide these global quantities. So the first is those solar sources, which is a satellite analysis from two different sorts of projects. One's called the Global Energy and Water Exchange Project's Surface Radiation Budget. And this project provides data from the early 1980s all the way through into around 2017, but our power provides through 2000. And after 2000, we provide data from the Clouds and Earth's Radiant Energy System series, which was on both the Terra and Aqua satellite platforms, and also now platforms from NOAA, including the SUMI MPP and the NOAA 20 satellite, and this instrument's being developed for future missions, new versions of it. So this is something that NASA is committed to, and this mission provides information about the radiative exchange at the top of the atmosphere and all the way through to the surface. And then from also in series, we have this fast long wave and shortwave radiative project called Flash Flux. And so all these projects together help us compute here, as depicted in this visual, the amount of sunlight that's transferred through the atmosphere through various cloud systems and reflected back to space, but also transmitted to the surface. And so that's what we're estimating and providing estimates for on a global basis from the early 1980s all the way to near real time. And then in terms of our meteorological data sources, NASA sponsors the Goddard Space Flight Center's Global Modeling and Assimilation Office. And this office does a modeling called a global atmospheric assimilation. And an assimilation uses a variety of satellite observations to essentially optimize model solutions. So a model forecast is produced and observations are used whenever they occur to optimize those, and then the model is rerun. And this iterative technique improves estimates of the surface quantities that are important for the energy and agriculture communities, such as surface temperature and water vapor quantities like dew point and relative humidity. There is estimate of winds through these atmospheric reanalysis products, and also precipitation. And so we have been able to utilize those and package those together with the solar irradiance and other quantities from the satellite Earth observations that we've mentioned, and then make those available as a package to these communities. And so we are featuring what we call the MERA 2, which is the modern retrospective analysis for research and applications, and also a near real-time version of that model, assimilation model called the FPIT, and we are featuring those two and for our data sources for meteorological quantities. So we provide these estimates of sunlight, so the amount of solar energy that's incident to the ground on a global basis for both time series and also long-term averages. So what I mean by time series is we feature, this is a depiction here of daily average, sequence of daily average images of the amount of sunlight hitting the globe. And so we have that for daily average time series, where users might want to use this for modeling of energy systems. And then, of course, we have long-term averages of that, which is depicted up here on the right-hand side here, which is a long-term average of those quantities. And so the long-term averages are useful for things like siting of various technologies and feasibility, how much energy is available on average. And so having the time series and the long-term averages allows users to understand the variability in time of these quantities. So now, the latest version, as I mentioned already, we now provide up to hourly for these data products, but we provide hourly for time from 2001 onward, but we also provide the daily, monthly, annual time series and the long-term average statistics. So one of the important things that we also do is we assess how good these parameters are. And that's very important for the users to understand their uncertainties. And this is just an example of comparing surface solar irradiance, the amount of sunlight incident to the ground, in this case for the daily averages, relative to a highly calibrated set of surface measurement sites that are distributed around the globe. And that network for this example is called the Baseline Surface Radiation Network, or BSRN. So here we have what we call a scatter density plot, but this just shows the amount of observations that agree very well with the estimates that we produce from our Earth observation data sources. And the statistics here, we have a very, very low bias and a very RMS that allows for people to use this with good confidence. We've also spent time to compare all those surface meteorological quantities to surface measurements from standard measurement weather sites. And we've done this through a feature we'll talk about, but this is another Esri story map. And this is an example of some validation figures that we feature within that map. And this is the validation of the MERA-2 observations against surface measurements. And there's much more surface weather measurements all around the globe. And each of these represents a different quantity. In this case, on the lower left, we have atmospheric temperature at 2 meters above the ground. And then we have minimum temperature at the bottom right and maximum temperature at the top right relative to that MERA-2 atmospheric reanalysis that I mentioned. And so you can go through and get a sense for each of these grid boxes have at least one surface site in them. And then you can zoom in. And if you're interested in particular locations, you can look at and interact with the data and understand what our estimate is and compare that to the surface measurement and get a sense for not only overall ensemble statistics, but for various statistics where you live. And so that's one feature, a tool that we'll be even developing, but this is a little story map that allows you to get an early look at this upcoming tool. But our main point here is we take the time to evaluate all our solar parameters and other radiative parameters like thermal infrared flux, the amount of energy from the atmosphere incident to the surface, through essentially temperature emissions of gases and clouds to the surface. But we compare those to the surface measurements and we compare our meteorological estimates to the ground-based weather site measurements. Well, as part of our new website, we also have what we call dashboards, and that allows users to understand the data sources and their current availability. And so these are called active in the sense that we're continuing adding to the amount of data from these data sources. And this first one, SRB, given their radiation solar for the early years, is inactive only because we're not building on that. We've stopped at December 2000 for now. But from there on, we use the series, what we call SYN 1 degree data product, and then that flash flux product to do up to near real time. And so we've strung those together to provide a picture of how the sunlight is varying. And then we use the MERA-2 and the FPIT for the meteorological quantities at the surface. So we provide that, and then we provide other dashboards showing the availability of the hourly data that we've mentioned. So you can figure out how old that is, 2 days from the FPIT, for instance, and also the daily data. And these dashboards are useful to trace the amount and the availability of data that's available and identify those sources. So how can one access the data products? Well, we have built into these latest tools 3 main ways. And the basic way is through what we call an API. And this API, or application programming interface, is essentially a URL type of code that's given that specifies your location and specifies what parameters you want, what dates you want them in, and you can get a direct return using an API response. Now that's for users that are a little bit advanced, but you can do that within a variety of tools such as ArcGIS software, or some have created interfaces for statistical packages like R. And you can do that within code like a Python code. And so you can access the data directly from an application. But we also provide what we call our own data access viewer, which utilizes the API, but guides the users more step by step of how to access and get the data. And then there's information about once you use the data access viewer, how to go back and utilize the API if you want to do repeated requests or repetitive quests for different areas. We also have been supporting and building up geospatial services, and we'll show some examples of those. And so we're providing a number of ways to access the data. So the first way is this data access viewer that really helps users get a orientation of how to provide the types of parameters that are available and how to provide them, how to obtain them, sorry. And so starting from the home page, you start from the home page, and then you scroll down and you go right to the data access viewer. And within the data access viewer, it'll come up, and there's a variety of applications, and we've now since added a couple more, including regional tools. But these apps allow you to obtain the data various different ways, and the default is this point application. So once you read over some of this and click it away, then you'll be left with this up here in the left hand. It's called the Power Single Point tool. So let's go ahead and allow this to go through. We access the data, and then we're going to choose. We have a number of decisions to bore down into the data to make a data request. And the first is a user community request. So we have gathered parameters and customized their units under renewable energy, and two other groups here would be available, would be that sustainable buildings and energy efficiency group, and then also agroclimatology. So once you pick your user community, then you'll pick what spatial temporal resolution you want. So do you want hourly averages, daily, monthly, annual, or long-term averages? So in this case, we're selecting hour, and we can use the point tool to select our location. Then we can select our dates. You can select arbitrary dates for all these quantities, even requesting your own climatology. Then you select a number of formats, and the formats is really where the community is supported in a number of ways. It used to be back 20 years ago that the ASCII was the only way people wanted the data. And then as the CSV, of course, as Excel gained popularity and more people utilized Excel, then we support that. But now with the geospatial tools, we support the formats of the GeoJSON and now NetCDF as people advanced. And then other communities have a few different other formats that are specific to their community. And that's one way that we support these various communities. So then you can come down and you can select various parameters. So in this case, we're selecting various solar parameters. There's temperature parameters as well at the surface. And then you can go ahead and submit. In our case, we selected CSV. And then so we'll get a Excel compatible data format and the
Hi, Paul.
in the file. Yes.
We have a clarifying question that just came through to me, asking whether or not this can be used in African countries and whether or not the data quality would be the same globally, including in Africa.
Well, we don't have a lot of surface measurements in Africa. We do have a few, and we've used what we've had, but we do have weather stations. So we definitely provide global parameters. So we do provide parameters in Africa, and we have validated them against the surface measurements that we possibly can obtain. So the answer is yes, we do have parameters. Yes, we have validated them, and we have some uncertainty information available. I'll show you where that is. but we do have sparse observations in Africa. So therefore, it's a little harder to gauge with such large distances between surface sites how accurate things are, but they do seem to be reliable. And I'm going to show some user stories in a little bit with an African case study. Okay, so here we just show the example here. We opened up the CSV file to show the hourly data products that were obtained by that data order. Okay, so then this describes our API. I mentioned that as kind of the foundation of how we obtain data products. And so this is in general how one could obtain a variety of different data products by URL command. And you can utilize this in scripts or your own software tools and directly obtain the data without leaving your tool. And so this depiction here on our website, we have a complete description and documentation how to form your API. Also, the data access viewer allows you to get examples of the API URL command that was used to obtain the data from your data access viewer order. And then this little video shows you that you can use a notebook called a Jupyter notebook that runs with Python, and then to work with this sort of interface, directly obtain the data and manipulate the data, do analysis as you need to do through this interactive tool. In this case, pulling forth various different parameters, making tables, and then later on you can make some figures and things with this code. All right, just an example there. And then we do have the GIS services. So we provide ArcGIS image and feature services. So this allows you to interact with the data for some of the visualizations that we've provided. And one of those is the what I already showed you, the evaluating data story. But also we have a number of other maps and other visualizations of the data products, which will hopefully be helpful to you. We do plan to expand this and make more services available, and also update some of these older ones. But these are featured on places like NASA's ArcGIS Online, or the Atmospheric Science Data Center at NASA Langley here in Hampton, Virginia, or even on the Esri Living Atlas. You can find examples of some of the power-based services that we've provided for users. And here's an example of one. We have been working with the ASHRAE User Industry Society. The ASHRAE stands, well, it's now incorporated, but it used to be the American Society of Heating, Refrigeration, Air Conditioning Engineers. And we have been working closely with them. They have a system, a definition for energy building climate zones, utilizing temperature in terms of heating and cooling degree days, and also precipitation. And so they have what they call their building climate thermal zones. And we were able to use our MERIT-2 observations and assess those. And so to get oriented, the coldest zones have the highest numbers and the hottest zones have the lowest numbers. So the very hottest and most humid zones are 0, and you can see those are in the tropics, and the coldest are up at the Arctic. And in this particular depiction, we derive those climate zones using a running four-year average period, or consecutive 4-year average periods. And so from the early 1980s, we can run through near day, and what you see is the variation in these 4-year periods of the zones. And you can see eventually that they begin to migrate northward in terms of the hotter zones. And so this is one thing that we're able to depict and visualize for the ASHRAE community. And another feature that we have in the website is what we call the Power Reports feature, where we provide information on the variability of a number of these parameters at the surface. And so here's an example of one report we have called the climate. This is actually the climate anomalies report. And in here, we list, we provide estimates of the mean. For instance, this is temperature at 2 meters. This is for climatology from 1984 to 2020. And this is for every month of the year. And the gray boxes give the mean temperatures, the red are given the maximum, and the blue are the minimum. And we have the variability of each of these in terms of min and max, and also the so variability of each class in terms of the min and max. And we also have the standard deviation as well as the mean values. And this is a web interactive, as you can see. Excuse me. So you can go point and click and actually get an estimate of these values in this report format, in this HTML-based report. So we have parameters like the temperature. Yes.
Sorry to interrupt again. I got another question come through on this. And the question is, are you seeing a warming trend in the data? And how does that affect the ASHRAE building climate zones and ultimately energy efficiency, building energy efficiency?
So one answer I'm going to show you here is at the bottom of this plot. And that is, this is for, we pulled the report here for London. And what we see is that London starts in the early years with a climate zone of about 5. And it's migrating this is according to our MERA2 products, but it migrated to a new zone, essentially to this 4 zone by the end of the period. And so the point is that there was a change that occurred. And so the idea of what these zones provide is they provide guidance for the building code specification. So in the US, everything that's built is built according to code, and your code is dependent on your climate zone. And so the colder you are, of course, you need to have more insulation and emphasis on your heating system. And of course, the warmer you are, you have to have an emphasis on the way you build your cooling systems. And so that determines your things, your actual building specifications. And that's why these codes are important. ASHRAE does collaborate with international codes. And so this shows a migration. So we do see an overall warming, but these zones are pretty wide. So most areas don't change zones. I'm going to show you a figure a little later that shows some differences between early and end zones. We do see some changes. One of the figures I didn't happen to have on me this time, but we'll put it on the website eventually, is the change in heating and cooling degree days. So that is a measure that the heating heating and air conditioning community uses to gauge how much heating or air conditioning you would need. They have a definition, a temperature threshold above which you would need to cool and below which you would need to heat. And so what we do find is complementary changes. We see that the number of days where heating is required is decreasing in a number of areas, and also the number of days where cooling is required is increasing. So we see complementary trends that way in certain areas, and so that is one way to trace that. So you can use this report on our website to find any location in the globe, and you can find the climate anomalies report, and you can pull that and see those sorts of anomalies. In fact, on this next page, I show some anomalies here, but these are just for solar irradiance. In this case, in London, the solar radiance has been relatively stable from the period of 1990 to 2014. And we provide some information about the values of that so we can interact with this report. You can actually get the various values. And this is an anomaly relative to the long-term average. So it shows the variability. You see the annual cycle, but you also see the year-to-year annual variability as well in the dark black. So we do provide that information in this report app. Well, how else have others utilized the data? So the access to the Power Web services are free and anonymous. So I wanted to emphasize that point. But we do try to keep track of how often they're used and where they're used and where data are used. So this gives a figure for the where the users were located, at least where their user IP was, their server was. It's not their exact location, it's just their general server, as compared to where they requested data for. So the data requests are in white, and the actually I can blow this up. Data requests are in white, and then red is the origination. This is for the month of September 2021, just for an example. So we have certain locations, and folks are requesting data for all over the world, and we're fulfilling orders for those locations. And you can see lots of African orders and lots of orders in South America and all the continents. And we do provide global. So we've had data orders in Antarctica to some of these northern locations in northern Canada and Greenland. So, and of course, Northern Europe and Siberia, Russia. So we have worked with a number of users, and I just wanted to kind of classify some of these users. I've already mentioned our relationships with the ASHRAE community, but we've also worked with the educational community where professors have used the website and designed class projects utilizing the data. So I think it's valuable for education. We've also had those in the agroclimatology use it for crop modeling, this group at the University of Florida, and also at World Agroforestry, for instance. And then we've also partnered with the with Natural Resources Canada's own Redscreen, which is a clean energy management software decision support tool, which can be downloaded, and there is an institutional fee for that, but it is available for inspection, and they can work with you. It is sponsored by the Government of Canada. We have worked with them, and we'll show some examples of some of the projects we've been able to support because of their expertise in the engineering part. This just depicts some of the applications that we know of. This is just a limited list of specific ones that we'll highlight here for the purpose of our talk and give you some examples. But we've colored the bullets with the various different communities to provide some examples here. And so this is a picture here of our heat map of surface long wave. Long wave is essentially the heat emission of energy from the atmosphere to the surface. We do provide that, and it turns out that that's important for buildings because they need to they have to include calculations of how that energy, the building cools naturally, and so this quantity actually turns out to be an important part of the building energy budgets. And so we provide this information to them, and you can see in this instance, this is the climatological map of each day and each month. So it gives the whole annual cycle of the downward long wave irradiance. But we support applications from solar cooking, solar sizing panels. We have some information on tilted solar panel. We provide these on monthly and annual basis, and now feature up to hourly observations. So one example here we wanted to highlight was this example in Western Africa. So we had this community in Western Africa that deployed the solar panel installation, and they were not getting the returns that they had expected. And so they hired a solar consultant who used our website to obtain climatological information for their region. And this chart shows the fact that we had from the satellite Earth observations a climatological average where they had a minimum of energy in the June to October timeframe. This was corresponded to their cloudy season, and they hadn't quite planned for that. They were thinking more in terms of the clear sky. And when they were looking at their charging, way they were charging and providing energy, they had underestimated the amount of panels they needed. We were able to provide this information. If we looked at the cloud fraction, it turns out that the daily average cloud amount was greater than 60% in 9 of the 12 months. So during this time where the direct normal irradiance was lower. So the consultant was able to work with the community. They were able to make some adjustments in the way they were using the power and billing for it, and they were able to move forward by understanding the amount of energy they'd receive in all sky conditions, that is cloudy and clear conditions. We've also worked with various different student groups to do things like, in this case, look at the sensitivity of developing renewable energies and the impact on the environment. So this student group used GIS tools. They used our solar insolation just as one of their parameters. And then they combined a number of other information from a number of other sources, including the land use and land cover change maps, high resolution maps of that. And they were looking at if they deployed solar with the environment or the vegetation species, or even you can see here such as the gopher tortoise and the American black bear, how sensitive would they be if there was a large deployment of solar technologies. So they were able to come up with a map that essentially showed some sort of sensitivity in their project. So environmental sensitivity versus solar suitability, and they were able to define their map based upon that. And then we had another project where they obtained high resolution mapping of the solar roofs in Satellite Beach, Florida. And then they were able to use that information and the orientation of those rooftops to estimate solar irradiance input. And they were able to find surprises, like you get more solar energy on the north side in certain months of the year than on the south side, even though Satellite Beach is such a southerly location. They also found that May was a better month for sunlight in Florida than June or July because of all the clouds in those months. So that surprised them, but they were able to utilize the information with the cloud information that we provide, and then use that climatological information and map that to the roofs. And we did provide some information on tilted solar irradiance as well, climatological averages there. And then they were able to use their other GIS information on the rooftops to estimate solar potential. And then this was the map I kind of alluded to before. This map is one of our feature services. And what we did is we compared the building climate zones that I introduced before from the period of 1984 to 1998 to the period 2004 to 2018. And what we did is we did a difference of those. And so if the difference resulted in a warmer zone, that's in red. So you get these ribbons and these turn out to be along the edges of the zones. So essentially the edges of the zones were found to be migrating north in the northern hemisphere and in Europe. There were some places where the zones actually did get a little colder according to this initial run. You can see actually some migration even in the tropical zones, and we had some that became wetter and drier as well. So you're able to utilize this map. I should be able to pull values for different places. We can also blow it up and to look. So if in fact, if we look here, United Kingdom, you can see here London, that did change. It's a little warmer zone here, but Glasgow hasn't changed the zone here according to this simulation here. So they're still in the original zone they were in the 80s. So that gives you a sense in terms of that. And then we've also worked with Redscreen, as we discussed. Redscreen is the world's leading clean energy decision-making software with over 732,000 registered users worldwide. And really, they've begun registering users by institutions. So there are multiple users within individual institutions. So we know that there's quite a number of worldwide users. And this figure shows various parameters here. And so Redscreen, we have worked with Redscreen. They have an automatic, when you do a climatological request for information, you automatically use either long-term averages from our website, or if you're doing monitoring of projects, which they support within Redscreen to evaluate your performance as a function of time, using time series data, they have a direct link to go directly and obtain the data from our website. You would go up to, say, select climate data, and you would have a direct link to the Power website. So this software provides energy efficiency, heating, cooling, power generation, a number of other applications. One of the users of Redscreen, and there are many, is the 3M Corporation, and they have many different plants, and they use Redscreen at all their plants, to 11 facilities, both in Canada and the US, to monitor their energy usage. We've also worked with this small company in Maine. It's called the Wicked Joe Coffee. And there's essentially a coffee beanery there, and they prepare the beans and cook the beans. And they found that by adding a solar wall to one of their walls, they were able to capture 40% more heating savings in the winter. Of course, being in Maine, that heating is their challenge. But they were able to save approximately $10,000 a year in heating costs with this modification to their building. And this building was done using Redscreen that utilized our Power data resources. And in terms of agroclimatology, this map is a similar map to one I showed last time, but now we're in terms of monthly averages for various different years. This is the 2-meter temperature. And so this variability is used in crop modeling because they're very interested in the temperature variation as a function of time for individual growing seasons, for individual crops. They also utilize our solar irradiance very heavily because that's not typically available for crop modeling. And they use other parameters such as precipitation. Is all very important for their simulations. And we provide our output in time series formats that is in their specialized format that's readily incorporated into their crop modeling. And this is one of the standard formats in the crop modeling sector. So, and lastly, just to highlight one example where we looked at changes in time. This was in the mid-US for corn yield. And this, we were investigating an increase of corn yield in the maize producing central US from the early 90s, late 80s and early 90s through to about 2010 or 2012. And they were trying to understand that. And it turned out that solar brightening, in other words, during that period of time, we saw an increase in the amount of solar irradiance during the growing seasons. And this spurred on the growth of the corn. This was independent of fertilization and irrigation and pesticides treatments of these plants. So it ended up being, on the whole, a 27% increase. This map that gives you various different levels of increase from the solar changes. We were able to use the power data derived over the United States to look at these changes. And we had some nice surface observations at various points, like one in Illinois, that we were able to confirm those changes. And so it made for an interesting study and showed some of the usefulness of having the time series information throughout those decades. So if you'd like to learn more about power, we've gone through a number of examples now. This presentation itself, there's a link. So besides being able to obtain this from the website in terms of the Resilience Hub, we also have a separate in our chat. You should see the link to this particular presentation so that you can review it whenever you need to. And also, we plan to put this on our main power website. We do have a complete set of documentation that does explain the various different products. So we have a methodology here, which also includes information on validation that I briefly mentioned during the talk today. And we do have these various dashboards to show the availability of data and the user metrics in terms of their use. And I just wanted to mention that if you are interested, we do have a 2-part webinar series that's available at the at NASA's RSET website. We have links here embedded, and this is an example of the homepage here. RSET is a remote sensing training program, and we actually go through this in even more detail in these two latter webinars, but all 4 are meant to highlight how NASA Earth observations are being utilized in the energy sectors to help promote that transformation that we've talked about earlier. Well, thank you so much for tuning in today and listening. And we'll certainly take some more questions. And Molly, I guess I'll turn it back to you for any comments and initialize our question answer session.
Yeah, thank you so much. That was a fantastic overview of what power can do. I do have a few questions that came through in the chat. The first one is, you mentioned that in Africa, there are very few stations. Can this data be beneficial to decision makers where there are very few observations in place? How does the data on meteorological variables compare to the observations?
For the most part, very well. We have that one group I mentioned at the University of Florida. They actually do active crop modeling in various areas around Africa, and they find very good reliability for the solar products in particular, and the temperature as well. Now they do use some other precipitation products. In fact, we are working right now to incorporate a new precipitation product to help provide some bracketing, but they are accurate enough. We've also had users, we had a Kenya user provide a complete map of Kenya for solar irradiance using the power data products. So we know that they have been used. We showed the one community site. So So we know that we have enough accuracy to be used for a number of projects, justify either funding of those projects, the feasibility of them, or monitor their performance in time. If you have a solar power panel farm or some sort of solar power plant, of course, there are other providers out there. These data are free and they are long term. So I do encourage this questioner here to look and see what else is available there. There might be some others, particularly if you have some other needs. But we do cover this 3+ decade time period, which does provide a nice long-term background. And when we can compare to surface observations, we feel they're well within a 10% agreement. Our current biases are less than 1% in terms of long-term averages, and even the daily averages, we tend to have a near a 1%. Less than 1% bias, but it does depend on areas. Some of the areas that are very prone to aerosols, there's higher uncertainty. So it does kind of depend where your particular region of interest is, because some of the biases depend on that. But for the most part, you'll find that they're very usable in these for all parts of Africa. So hopefully that answers the question.
Yeah, great. And maybe Paul, just to riff on that question just a little bit, do you think that in terms of the types of decisions that can be made, that this is, given the uncertainty, that this product might be better suited for planning? Or I know that you had real-time data as well. What types of decisions do you think that this information would be most useful for in data sparse areas?
Well, I think that is the key. I think that it's useful for the feasibility of particular projects in particular areas. We noted this one Western African community where they had installed, based upon essentially solar geometry, just how does the sun vary through the year, and not really taken into account their weather conditions and their cloud conditions. So, and this was more than accurate to help that community better understand their solar resource and how it varies typically throughout the year. So feasibility is clearly one of the areas. We have the information down to the monthly scale, of course, and even I mentioned daily. So you can really assess the variability in time at your particular location, and assess also whether or not you're seeing any changes. So we should be good enough to sense some changes in some of these areas as well, and particularly large changes. So if the cloud patterns have changed significantly, you'll see that in the statistics if you compare the long-term variability. So feasibility is definitely one area. And then the monitoring, the near real-time time series does allow you to monitor and allows you. So a number of users we've had, I didn't show an example of this, but we've had users compare the output of their solar panel systems on a daily basis to the estimated irradiance, and they have seen that the correlation of those two is so strong that when they get some sort of degradation in their panels, maybe they're covered with dirt or there's some other problem, they're actually able to detect problems and make some adjustments. We had one provider have a solar irradiance measure right next to their solar panels, and they were monitoring our estimates compared to their measurement, and noticed that the measurement was disagreeing by larger and larger amounts with our estimates. And then they were able to find out that it was their instrument that was the problem. And so we do have enough long-term precision that it's reliable to look at certain problems with systems and verify that things are working properly. So that Redscreen tool I mentioned, that actually makes a model that's dependent only on weather conditions. And of course, there's some engineering details of your solar system and its size and those sorts of things. It takes all that into account, but it makes a model based on weather and solar conditions. So if you have a building that really depends on that information, and you want to look and target different technologies to see if you can improve your energy, reduce your energy usage, you can use that tool and the actual weather conditions to assess and target which sort of technologies might make an impact that would provide for feasibility or payback in the longer term. So that's a very useful tool. And when you install that technology, then you can use it in a monitoring sense to see, okay, well, given the actual weather conditions, I can use their model of my old performance, and now I have my new performance. So now I can estimate how much I'm actually saving relative to those weather conditions. So the Redscreen tool is very powerful in terms of both monitoring and in terms of feasibility. And that's what we see people using the data products for.
Great. Thanks, Paul. I just had one more question. Do you have any future plans to incorporate climate change models to inform future long-lived energy investments?
Yes, we actually do have those plans. We're starting this year. Now that we've released this latest version, we now have the customized data products for the various communities. And so our idea is to begin to pull, and we have some expertise both at NASA and with some partners to pull the climate observations from the CMIP-6 and look at it in terms of various different scenarios. We have, of course, there's a number of models represented in the CMIP-6, so we'll try to provide some sort of percentile change, but we would like to do, our goal is to pull that data in and look at providing these sorts of outputs in the same sorts of formats or same sorts of parameters that we have and reports that we feature now on the Power website. But we're looking at certainly at least probably a year or two out on doing that.
It's great that you'll be bringing in the CMIP-6 models. I know that will be a nice addition to what's out there right now. Most of the information is CMIP-5. I guess I don't see any further questions. I just want to wrap up and thank you so much for your really insightful presentation. And I think that, as Laura mentioned from the outset, there's just a massive opportunity for this information to basically support renewable energy and agricultural decision-making globally in a way that it is necessary now if we're going to be able to achieve scale. And especially in data sparse areas, this information will be particularly valuable. And I appreciated the examples that you shared globally. So really demonstrating the power of NASA Power information. So thanks again for your presentation. It was really insightful.
Well, thank you, Molly, and we do appreciate that. And we are open. Just encourage anyone here that listens to continue to ask questions. We have actually, we do have a, should have shown that at the bottom, emphasize their email address. If you have questions, at the very bottom of our presentation here, we have an email address where you can email us directly and get more information. And we can certainly point you to, if we have the information online, you can see it in our docs pages. I encourage you folks to take a look at those, but you're always welcome to ask questions, and we'll try our best to answer those questions as quickly as we can.
That's fantastic. I should have mentioned that there is support available to use the tools, right?
Yes, that's right.
Okay.
And we provide user support, and we're building up frequently asked questions for other questions. We have a forum as well that questions can be answered in. And we have this direct email that you can ask your questions, and we will respond as quickly as we can.
Thanks again, Paul, and thanks the audience for tuning in. Really appreciate the time and effort that you spent today in informing us about this wonderful tool. Thanks again.
Thank you. And thanks everyone for your attention.